Thank you for organizing this virtual voice symposium. I'm very glad to be here. The topic of discussion today is how the deep neural network can be realized for automatic pathological voice quality evaluation. Here is the outline of my presentation. Auditory perceptual evaluation is a method in which a doctor or speech therapist evaluates a patient's voice quality based on auditory impressions. GRBAS Scale is the most widespread evaluation method. GRBAS Scale was developed in Japan and is used worldwide. The scale consists of 5 items: grade, roughness, briskness, asthenia, and strain. For each item, a score of 0 to 3 is given. 0 means healthy, 1 means slight, 2 means moderate, and 3 means severe. Since voice quality is determined by human hearing, so auditory perceptual evaluation is the gold standard for voice quality assessment. However, there is an inherent problem with GRBAS Scale. GRBAS Scale lacks reproducibility because of inter- and intra-rater variability. Therefore, in order to solve this problem, we worked on developing artificial intelligence, or AI, to automatically evaluate GRBAS Scale. In our study, the AI learns the doctor's hearing. The AI with the doctor's hearing can evaluate the GRBAS Scale with complete reproducibility anytime, anywhere. We think that this AI will help in speech medicine. So here is the design of this study. The task is the classification of the scores of GRBAS Scale. We adapted the deep neural network, or DNN, as the AI algorithm. The DNN inputs spectrograms of sustained vowels R and outputs GRBAS scores. Until now, 2 groups have been working on the automatic evaluation of GRBAS using DNN. Our study differs from theirs in terms of inputs. Now, let's talk about our method. Earlier, I didn't mention how the AI learns. The AI learns using a dataset of pairs of voice and GRBAS scores. So we started by creating a dataset. First, we prepared the audio data. Sustained vowels were extracted. The sampling frequency was set to 48 kHz. Audio samples were recorded at the Kyushu University Hospital and Kyushu University Ohashi campus. The sample size was 3,118, and the number of speakers was 1,545. After preparing the audio data, one skilled laryngologist rated the GRBAS scores for each voices. Here is the overview of our automatic system. Let's start with the spectrogram we used in our experiment. The spectrogram is a time frequency representation of a sound wave. In other words, it is a combination of spectra on a time axis. In our study, we specifically used what is called a mel-frequency spectrogram. I will explain what mel is. The mel scale is a perceptually proportional scale of pitch based on human hearing. Human pitch perception has been suggested to be logarithmic by psychological experiments. Based on this finding, the frequency axis of the mel-frequency spectrogram is logarithmically compressed. This left figure is a heat map of the mel-frequency spectrogram of a sustained vowel R. The horizontal axis indicates time. The vertical axis indicates frequency, and the brightness indicates the strength. You can see that the frequency axis is logarithmic. The right table shows the calculation condition for the mel-frequency spectrogram. Let me explain about the structure of the DNN in our experiment. The DNN inputs spectrograms and outputs the probability of each score for each GRBAS item. The DNN was composed of a recurrent neural network and a multiple layer perceptron. Recurrent neural networks can handle time series features. Spectrograms are time series information, so we adapted a recurrent neural network. The multiple layer perceptron was introduced for further feature instruction. Here is a concrete structure of the DNN. We've created a model for several different numbers of layers. This is the deepest model. Speaking for engineers, we introduced dropout and batch normalization to prevent overfitting and promote learning. The symbol N is the parameter for the node size of layers. This table shows the DNA parameter settings. Speaking for engineers, L2 regularization and gradient clipping was introduced to suppress gradient explosion and overfitting. Again, here's the overview of our automatic system. Now let's move on to the results. At first, we will explain the performance measures we used. We used accuracy and linear weighted kappa as performance measures. Accuracy is the proportion of exact agreement between two raters. In our case, one of the raters is a laryngologist, and the other is a DNN. Linear weighted kappa indicates the strength of agreement between two raters for original scale data. This indicator takes into account the agreement occurring by chance. The benchmark for linear weighted kappa is given as shown in this table. Before we show the performance measures, please take a look at this figure. This figure shows the distribution of the dataset. The dataset was imbalanced, especially for item A. Let's get into the performance results. We did 5-fold cross validation to evaluate the performance. In 5-fold cross validation, the performance is evaluated by the dataset divided into 5 parts. This table shows the performance results. The values in the table are the average of values obtained by 5-fold cross validation. The accuracy was 60% on average. The linear weighted kappa was moderate for items G, B, A, and F, and fair for item R. Here are the detailed results for one of the 5-fold cross validation. This table is commonly called a confusion matrix. The rows indicate the doctor's score, and the columns indicate the DNN's score. For example, the value of 227 here indicates that there were 227 samples that the doctor rated as G1 and the DNN rated as G1. So the diagonal lines indicate the number of exactly matched samples. Here are the performance measures. As a typical result, let's compare item G and item A. For the accuracy, item A is higher than item G, but for linear weighted kappa, item G is higher than item A. Our dataset was imbalanced, especially for item A. Thus, the agreement by chance was more likely to occur for item A. The linear weighted kappa reflects this imbalance. The DNN tended not to output scores with relatively small sample sizes. Now, we will discuss the results. There is a trade-off between the frequency resolution and the time resolution of spectrograms. This trade-off might make it difficult for the spectrograms to sufficiently represent fluctuations in the fundamental period and amplitude. Also, it has been suggested that item R is correlated with fluctuation in amplitude. Therefore, we think some input features that explicitly represent fluctuation might be effective for performance. We believe that we can further improve performance. Last slide, please. We constructed a DNN that outputs the GRBAS scores with spectrograms of R as an input. The estimation performance was moderately good. In the future, we would like to improve the performance by exploring other input features and the structure of DNN. We also think it is necessary to investigate the validity of the automatic evaluation compared with the doctors and speech therapists. We are aiming at the clinical application of automatic evaluation with AI. Thank you.